To understand our next topic, which is called logic gates, one must first understand the basics of the two major types of electronic circuits, namely analog circuits and digital circuits. So let's first look at what is exactly an analog circuit. An analog quantity is a quantity which can vary continuously within certain limits, of course. And in analog circuits, the input voltages given to the circuit as well as the output voltages obtained from it are analog in nature. That is, they can vary continuously within some limits. As an example of an analog circuit, let's consider an amplifier whose voltage gain is equal to 100. So on the left hand side, these are the input terminals of the amplifier, and the input voltage applied across these terminals, let's imagine it to be a sinusoidally varying voltage like that. Maybe its amplitude is Vm. So the maximum value it can reach is Vm, the minimum is minus Vm. So essentially at the input of this particular amplifier, we have got a voltage which can take any value and which does take any value from minus Vm to plus Vm. In other words, at the input of this amplifier, we have got an analog voltage. Now this input voltage is multiplied by 100 and it appears across the output terminals like this. So this peak value should be 100 times Vm, and the negative peak value is of course going to be minus 100 times Vm. Now once again, the voltage across the output terminals is an analog voltage because it continuously varies from one value minus 100 Vm to another value 100 Vm. And so because both the input as well as the output voltages of an amplifier are analog in nature, an amplifier is a very good example of an analog circuit. Other examples of analog circuits which you have studied are oscillators and rectifiers. Now, on the other hand, in certain electronic devices like calculators, computers, and so on, the voltages involved in the circuit are not analog voltages because they are not continuously variable. Rather, the voltages are allowed to take certain specific values only, and such quantities which cannot vary continuously but rather they are allowed to take only certain specific values, these quantities are called discrete quantities. The difference between analog quantities and discrete quantities is a bit like the difference between the wave theory of light and the quantum theory of light. We know that in the wave theory of light, when light falls upon a surface, the surface can absorb any amount of energy. So there is no restriction on that. But according to the quantum theory, the surface is allowed to absorb energy in certain discrete packets which are called photons. And in the type of circuits which we are currently discussing, there are only two specific values of voltage which are allowed. Such circuits in which only two values of voltage are allowed are known as digital circuits. So in contrast to an analog circuit where voltages involved can vary continuously, in a typical digital circuit only two values of voltage will be allowed, both at the input as well as at the output. Now, the exact two values of voltage which are allowed in the digital circuit would actually depend upon the type of circuit. However, just to simplify things, let's make an assumption, namely that in the given digital circuit, the two allowed values of voltage are 0 volts and 5 volts. In other words, any input voltage or output voltage in the given digital circuit can be either 0 volts or 5 volts. It cannot take any third value. Please note that in saying this, we are simplifying things. In reality, in a digital circuit, there would be two ranges of voltages involved rather than two exact voltages. However, for our purposes, this particular simplification is quite okay. Now, the fact that you can have only two voltages in a digital circuit has a connection with a certain branch of mathematics which was developed by the English mathematician, logician and philosopher George Boole in 1854. This branch is called Boolean algebra, and it is connected with mathematical logic. In Boolean algebra, you have only two values, namely 1 and 0. They are sometimes called true and false, and on other occasions they are called on and off. And the operations which we use in Boolean algebra are also not the normal operations which we use in algebra, like addition, subtraction, division, multiplication and so on. Rather, they are special operations, and the names of a few of them are and, or, and not. In fact, Boole's 1854 book, in which he published his research in this field, was titled An Investigation of the Laws of Thought, and the name suggests to me that when Boole discovered his algebra, he was trying to figure out the rules governing logical thought. Now we will look at these operations and, or, not and so on in more detail later, but currently let us just take one simple example. The idea is that operations such as these can be applied to values which can be either 1 or 0, and the result of such an operation will depend upon what are the values you are using and also what is the operation involved. For example, let us consider two variables, two logical variables, P and Q, and let's conduct the operation OR on these two variables. So my Boolean expression or my logical expression is P or Q. You can see that this Boolean expression looks like a normal algebraic expression, for example x plus y, and just as the value of the expression x plus y would depend upon the value of x and the value of y, the value or the result of the Boolean expression P or Q would depend upon the value of P and the value of Q, each of which can be either 0 or 1. And since we are taking a very specific example, let us consider the case where P is 1 and Q is 0. Now in that case, the operation of OR gives the result of 1. That is the way that the logical operation OR has been defined. Now there is a reason why it has been defined that way, but the reason will be clear a bit later. Currently, you just accept that if P is equal to 1 and Q is equal to 0, then the Boolean expression P or Q gives an answer of 1. Note that some people, instead of the symbols 1 and 0, use the symbols true and false. So they would say that when P is true and when Q is false, the Boolean expression P or Q yields an answer of true. Note that when P is 1, Q could be either 0 or 1. And similarly, when P is 0, Q could once again be either 0 or 1. And so, there are totally 4 possibilities depending upon the values of P and Q. And corresponding to each permutation of P and Q, we have a well-defined answer, which of course is going to be either 0 or 1. In the example which we have just set up, when P is 1 and Q is 0, P or Q is equal to 1. So all of this was to give you a very basic feel for Boolean operations and Boolean values. Now we turn to the connection between Boolean algebra and digital circuits. Remember, in Boolean algebra, there are only two possible values for variables, namely 1 and 0. And likewise, in digital circuits, the voltages involved could have only one of two possible values. And remember, we have made the simplifying assumption that these two voltages are 5 volts and 0 volts. So we assign the two Boolean values of 1 and 0 to these two voltages. For example, the Boolean value of 1 can be assigned to the voltage of 5 volts, and the Boolean value 0 is assigned to the voltage 0 volt. Note that the allotment could be done the other way around, that is 0 could be assigned to 5 volts and 1 could be assigned to 0 volts, but we will assume this particular allotment for the purpose of the example. So once again, 5 volts corresponds to the Boolean value of 1 and 0 volts corresponds to the Boolean value of 0. So this tells us how to take care of the Boolean variables like P and Q in a digital circuit by representing their values either by 0 volts or by 5 volts. This is the first step in establishing the connection between Boolean algebra and digital circuits. Now comes the second step. There are available various digital circuits made of a combination of transistors, diodes and resistors, which perform the logical operations or functions AND, OR, NOT and so on. For example, It is possible to fabricate an electronic circuit composed of resistors and diodes, which performs the job of the OR operation. And such electronic circuits are in general called logic gates. And this particular circuit which I just now talked about would hence be called an OR gate. Now, we do not want to get into the intricacies of how these electronic logic gates are actually made, and so we are going to represent the electronic OR gate of this particular example by a simple block diagram as follows. This OR gate has two input terminals like this, and they represent P and Q. For example, let the top input terminal represent the Boolean variable P, and let the bottom one represent Q. The OR gate has a single output terminal like this, which represents the result of the Boolean operation P or Q. How does the OR gate function? Remember, when the Boolean variable P has a value of 1 and the Boolean variable Q has a value of 0, then the result of the operation P or Q is equal to 1. Further recall that the Boolean variable 1 is represented by a voltage of 5 volts and the Boolean variable 0 is represented by a voltage of 0 volts. In other words, this particular electronic circuit is made in such a way that on the top terminal on the left hand side, when you apply an input voltage of 5 volts, so I'll write 5 volts over here, and on the second or the bottom input terminal you apply an input voltage of 0 volts. Both of these voltages being measured with respect to a common point in the circuit, which is usually called the ground. Then the circuit automatically gives a voltage of 5 volts at the output terminal. Remember, there are other permutations of P and Q possible, but the circuit is made in such a way that whatever be the value of P and whatever be the value of Q, the circuit will consistently give an output which corresponds to P or Q. And this, in short, is how the Boolean operation P or Q is carried out in practice in an electronic digital circuit known as an OR gate. But that's not the end of the story, because for every other Boolean operation too, like AND, NOT, and so on, you can build a corresponding electronic circuit. And this tells us that there is a one-to-one correspondence between Boolean expressions contained in Boolean algebra and digital circuits. Now that we have understood the basics of Boolean algebra and digital circuits, we can go on to study in some detail various logic gates. So, some general facts about logic gates first. Remember, a logic gate is an electronic circuit which can have one or more than one input terminals, but it always has exactly one output terminal. Also remember that each input can be either 1 or 0. What this means is that if there are n input terminals, then correspondingly there can be 2 raised to n different permutations of the input values. Also note that the output value can also be either 1 or 0, and the logic gate is made in such a way that for every permutation of these input values there will be a specific output value which will be either 1 or 0. It's a bit like a function in calculus. That is to say, if I have a function of, let us say, 3 variables x, y and z, then the value of the function for 3 particular values of x and y and z will be very specific, and it will basically depend on x, y and z. Now, corresponding to every logic gate, we can draw a table which is known as the truth table of that logic gate. So I'll just draw a diagram representing any general truth table like that. Now, every truth table can be split into 2 parts by a vertical line like that, and this part of the truth table will contain the inputs in the form of one permutation of input values per row. For example, if the given logic gate has only 3 input terminals, then the first row might contain the permutation 0, 0, 1, the next row might be 0, 1, 0, and so on and so forth. Now, needless to say, for a logic gate having n input terminals, the number of rows in the truth table corresponding to that logic gate will be 2 raised to n. The other part of the truth table, that is this part, contains the output. That is to say, corresponding to every possible permutation of inputs. For example, look at the first row where you have got 0, 0, 1. You have to write in this particular column either 0 or 1, any one of them. It's going to be either 0 or 1. It has to be very specific, and it will depend upon the type of logic gate. So needless to say, since there are 2 raised to n rows corresponding to 2 raised to n permutations of input values, there will be 2 raised to n output values in the truth table. We will now study in some detail certain specific logic gates, and we will start with the AND gate. The AND gate can have 2 or more than 2 input terminals, but for the sake of the example we will be considering an AND gate having only 2 input terminals. Any AND gate, irrespective of the number of input terminals, will always have exactly one output terminal like that. Let the inputs be A and B. The output, of course, is going to be A and B. Note that A and B is sometimes written as A dot B, where the dot stands for AND. Also, instead of drawing a box with the word AND written inside, we will use the universally accepted standard symbol for an AND gate, and this symbol looks like this. Now we will proceed to write the truth table of the AND gate. So the truth table will have 2 sections. This is the input section and this is the output section. and in the input section there are going to be two columns, one for A and the other for B. In the output section, of course, we are going to write A dot B or A and B, and we can even give it a name. Let's call it Y. Now A and B can each be either 0 or 1. So at a later stage I will finally write this truth table using zeros and ones. But in my opinion, it is easier to understand this truth table if we use the symbols true and false instead of 1 and 0 respectively. So we will first draw the truth table using the symbols true and false, and later on we will replace them with 1 and 0 respectively. Now let's begin by writing all the possible permutations of A and B in terms of true and false. So one possibility is A is false and B is also false. While writing the next possibility, I will retain A as false, but I will change B from false to true. So I have false and true. Now we note that both possibilities involving A as false have been taken care of. False false and false true. So we have no option but to change A from false to true and write the third possibility like this. So A is true. I'll start by writing B as false. And in my final and last possibility, I retain A as true, but I change B from false to true. So I have these four permutations: false false, false true, true false, and true true. Now note that this is a standard sequence of writing the permutations. When you write them in terms of the digits 0 and 1, false becomes 0 and true becomes 1. So you would be writing false false as 0 0, followed by 0 1, followed by 1 0, and finally followed by 1 1. Now for convenience and for ease of understanding, let's look at the last row in the truth table. What I want to do is to find out what is the value of A and B if A is true and B is also true. To do that, I am now going to write two individual statements which I will call A and B. So statement A is Mumbai is on the west coast of India. Now clearly statement A is true. Following this, I will write another statement which I will call B, and that statement is Pondicherry is on the east coast of India. Now clearly this is a situation where statement A is true and statement B also is true, and so without doubt we are talking about the last row of the truth table where A is true and B also is true. Now let me try and write the sentence corresponding to the Boolean expression A dot B, which of course stands for A and B. Naturally the statement is going to be Mumbai is on the west coast of India and Pondicherry is on the east coast of India, which we now write as follows. Now we have to ask ourselves the question, is this sentence taken in its entirety true or is it false? In other words, if somebody says this entire thing, Mumbai is on the west coast of India and Pondicherry is on the east coast of India, is that person being truthful or not? Now obviously the answer is yes, this is the truth. and that is the reason why the value of A and B, when A is true and B is true, has to be true. Now, in contrast to this, when any one of these statements is false, then the entire sentence made by connecting them with the word and must necessarily be false. And let us illustrate this with an example. So to do that, we'll have to modify statement A. I'll rub out west, and in its place I write east. So the statement A, namely Mumbai is on the east coast of India, is obviously false. Statement B still is true because it's the original statement. Now look at the entire statement made by combining the two statements. I have to change this west to east like that, and now ask yourself the question, is a person who makes this entire statement, that is Mumbai is on the east coast of India and Pondicherry is on the east coast of India, is this person speaking truthfully or not? And the obvious answer is no. In other words, this entire sentence, if you look at it as a whole, this statement on the whole must be false. And this brings us to the second row of our truth table. You can see A is false, B is true, and so obviously A and B must be false. Now likewise, if the first statement A is true and the second statement B is false, then A and B must be false, and that leaves us with the first row in the truth table where A is false and B is false. That's trivial, but let's go through it all the same. So I start by reading statement A, Mumbai is on the east coast of India. That's obviously false, and that's what I want. Now I want B to be a false statement, so I just change it like that. Pondicherry is on the west coast of India, obviously false. So read them together. Mumbai is on the east coast of India and Pondicherry is on the west coast of India. Obviously the entire statement is false. So this is the truth table corresponding to the Boolean expression A and B, and all I have to do now is to replace false with 0 and true with 1. So I'll start with the first row. False, false, false becomes 0, 0, 0. In the second row, false, true, false becomes 0, 1, 0. In the third statement, true, false, false becomes 1, 0, 0. And finally, in the last row, true, true, true becomes 1, 1, 1. In other words, the value of A and 1 is equal to 1 if and only if A is 1 and B is also 1. In any other case, and there are 3 of them, the value of A and B must be false. It must be mentioned that an AND gate can have more than 2 input terminals. As an example, let's consider an AND gate which has 3 input terminals like that. Now the truth table of any AND gate follows the same rule, namely if all of these inputs are equal to 1, that is the only case when the output of the AND gate is going to be equal to 1. In all other cases, the output of the AND gate is going to be equal to 0. So if you are asked to write the truth table of this particular 3 input AND gate, then the first thing that we could have done is to name these inputs, let's call them ABC, and the output is Y, and the truth table will once again contain two sections. One will contain ABC, which is the input section, and Y, which is A and B and C, is going to be the output. So over here in this region of the input table, we write all possible permutations of A, B and C. Now there are going to be, of course, 8 possible permutations. There will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. So if you count them, you get 8 rows. And now when we write the output of this truth table, it is only in the last row where A as well as B as well as C are 1 that the output is going to be 1, and in all other cases the output of the truth table is going to be equal to 0. So that is the general way to write the truth table of any AND gate. And with this point we complete the discussion of how an AND gate works. And so we can go to the next gate, and that's the OR gate. Once again, like in the AND gate, we will study a specific example of the OR gate, which contains two input terminals, and we of course must bear in mind that an OR gate in general can have more than two input terminals. There will always be, however, exactly one output terminal. So let's begin by drawing the standard symbol for an OR gate. It looks like this. It has one output terminal over here, and since we are taking a specific case where there are only two inputs, we are going to show two input terminals, one here and the other here. Now let's assume that the two inputs which you give to the OR gate are A and B, and naturally the output, which I can call Y, is going to be A or B, and the symbol for this OR is plus. So it's a bit confusing. I have to write in place of A or B, I'll write A plus B. So I'm not adding them. This plus doesn't mean add. It's just a symbol for the Boolean operation OR. You have to just remember it. So let's now draw the truth table of the OR gate. So as usual, we won't start by putting zeros and ones in these places. What we'll do is we'll convert the zeros to false and the ones to trues. So false false, false true, true false, and true true are the four possible permutations of A and B. So I, as usual, start with my two standard sentences, and I've written them in such a way that both of them are true. A. Mumbai is on the west coast of India, true. B. Pondicherry is on the east coast of India, also true. And now I'll write the sentence which is symbolized by A or B. It's Mumbai is on the west coast of India, or Pondicherry is on the east coast of India. Now in the English language, the word or can be used with two different meanings. Firstly, it can mean, in this context, either Mumbai is on the west coast of India or Pondicherry is on the east coast of India, but both cannot be true. Now that's one way to use the word or. The second way is the way it is being used right now, that is, it's either this or that or both. So what this or means over here is either Mumbai is on the west coast of India or Pondicherry is on the east coast of India, or both. So whenever the word or is used in Boolean algebra in isolation, then you have to interpret it in the second way, meaning either the first statement or the second statement or both statements are true. It's a bit like a school. Let's imagine that there is a school and it is giving admissions to children in the nursery, and the school sends a letter to the parents saying during the time of the admission the child must be accompanied by the father or the mother. Now the word or in that letter is, what's the meaning of that? It's either father or mother or both. That is to say, even if the child is accompanied by father as well as mother, the child will be considered for admission. Now let's return to this sentence. Now if somebody says this entire thing, he means either Mumbai is on the west coast of India or Pondicherry is on the east coast of India, or both are true. Now is this statement, the entire statement, true or false? Is this person speaking truthfully? The answer is obviously yes. And that's why in the last row of this truth table, A is true, B is true. Obviously A or B must be true. Now let's go to the next case, and we will purposely now make statement A false. So I'll scratch out the word west and I'll put east there. The sentence reads Mumbai is on the east coast of India. It's obviously false. B is the same as before. It's true. Now let's read the sentence in its entirety. Mumbai is on the east coast of India, or Pondicherry is on the east coast of India. It means either this is true or this is true or both are true. Now it's pretty clear that since this is true, the person who says this thing is being truthful, because when A or B has to be true, then it's either A is true, A alone is true, or it's B alone is true, or it could be A and B are both true. In this case, the first sentence A is false, but the second sentence B is true. And that's why when somebody makes this statement, Mumbai is on the east coast of India or Pondicherry is on the east coast of India, we consider the second part of the sentence, which is definitely true. Pondicherry is on the east coast of India, and so the entire statement is true. So that would be the second row of the truth table. A is false, B is true, A or B must definitely be true. Now likewise, if A is true and B is false, once again A or B must be true, and that leaves us with the very first row. Let's imagine that a person makes a statement where he says Mumbai is on the east coast of India or Pondicherry is on the west coast of India. Now he has made two false statements, one after the other, connected by the word or. None of them are true. Now this person would have been taken to be speaking truthfully if only the first statement was true, or if only the second statement was true, or if both of them were true. None of these cases is fulfilled because both of these statements are false. So obviously the person is not speaking truthfully, and in the first row of this truth table, when A is false and B is false, A or B must definitely be false. So all that remains now is to express this truth table using ones and zeros. So as usual, we will replace false with zeros, and we will replace trues with ones. So we finally get this type of truth table, and we can actually see very easily that the value of A or B is 0 only in one case, and that is when A is 0 as well as B is 0. In all other cases, the value of A or B is equal to 1. Now, an OR gate, just like an AND gate, can also have more than two inputs. And to understand how to draw the truth table of such an OR gate, let's consider a simple example of a 3-input OR gate, which looks like this. Now let's name the inputs A, B, and C, and name the output Y. Now the simple rule for this particular OR gate, even if it has 4 terminals or 5 input terminals, the rule is still the same, and the rule is the output Y is going to be equal to 0 in only one case, and that case corresponds to all of the inputs. In this case there are 3 of them being equal to 0. In all the other remaining cases, the output Y is going to be equal to 1. So if you are asked to draw the truth table of such an OR gate, the first thing of course one has to do is to set up the input part of the truth table, which will have 8 rows, because there are 8 permutations of A, B and C starting with 0, 0, 0 and going right down ending at 1, 1, 1. The output now has to be written. Remember the rule: when all of A, B and C are equal to 0, that's in the first row, that is the only case where Y is going to be equal to 0. In all other cases, since there is at least one of the inputs A, B, C being equal to 1, in all the other cases the output Y is going to be equal to 1. So that's the simple rule to find or to draw the truth table of any general OR gate. And with this we complete our discussion of how an OR gate works. Our next gate is called the NOT gate, and it's a very simple gate to understand. The symbol for a NOT gate is like that. It's a triangle, and over here you have a small circle. A NOT gate will have only one output as expected, but what is peculiar to a NOT gate is there is exactly one input. So a NOT gate has one input and it has one output. Now this one input which you provide to the NOT gate, let's call it A. The output which you get from the NOT gate, we can call it Y, and the symbol for the output of a NOT gate, of this NOT gate, is A with a bar on top, and it's called NOT A. So NOT A is symbolized by A bar, and the word NOT A actually tells you how the NOT gate operates. For example, if the input A is equal to 0, then the output is not A, which means not 0, and so the output must be 1. On the other hand, if the input to the NOT gate is 1, then the output, which is not A, must be not 1, which is 0. In other words, whatever value you feed in to the NOT gate is going to give you as an output the complement of that value. And the truth table of a NOT gate is also quite simple. In the truth table, as usual, you're going to have two regions. One is for the output and this one is for the input. Now the input is called A, the output Y is equal to A bar. Now how many rows will the truth table have? Obviously it will have only two rows, one for A equal to 0, the other for A equal to 1, and when A is equal to 0, A bar is equal to 1. When A is equal to 1, A bar is equal to 0. So that in short, is how a NOT gate operates. Our next logic gate is called a NAND gate, and a NAND gate is actually an AND gate which is followed by a NOT gate, like that. So it means that the output of the AND gate is given as an input to the NOT gate. Now the overall NAND gate could have two or more than two inputs, but for simplicity I am going to assume that there are only two inputs. So this entire structure, it becomes a NAND gate, and of course when we draw the truth table of a NAND gate, the rule is very simple. Whenever this particular AND gate is expected to give an output of 1, the NOT gate is simply going to invert that or to convert it into a 0. And on the other hand, when the output of the AND gate is equal to 0, the NOT gate is going to convert it into a 1. So if you know how to draw the truth table of an AND gate, you can easily draw the truth table of a NAND gate by converting zeros to ones and also simultaneously converting ones to zeros. Of course, there is a standard symbol for the NAND gate. It's not usually drawn like this. The symbol is, you start drawing an AND gate and you put a small circle over here which corresponds to the NOT gate. So this is the output, and since we are currently considering a 2-input NAND gate, we draw 2 input terminals over here. So this is the symbol or the diagram for the NAND gate. Note that the word NAND has been derived from NOT, that's the N, AND. So NOT AND is NAND. And let's now try to draw the truth table of this particular NAND gate. Let's call the inputs A and B, and the output is Y. Now Y is actually A NAND. The operation is NAND B, A NAND B, and the symbol for A NAND B is, you first draw a bar because the bar symbolizes NOT and it's NOT of AND. So below the bar sign you write A and B or A dot B. So this is the symbol for A NAND B. Now the truth table of this 2-input NAND gate is of course going to contain 4 rows because there are 4 permutations of A and B, and those permutations are of course 0 0, 0 1, 1 0 and 1 1. And now we try to write the output, which is Y, which is A NAND B. The trick of course in writing the output is to first assume that this bar is absent. In other words, treat it as a normal AND gate, and you know that for an AND gate the only place where you're going to get a 1 is over here, and everything else is going to be equal to 0. Now of course we are trying to draw the or write the output of a NAND gate and not an AND gate. So wherever you find 0, you just convert it into 1, and likewise the 1 gets converted into a 0. So that's the general rule for drawing the truth table of a NAND gate, which is whenever all the inputs are equal to 1, that is the only case when the output is equal to 0. In all other cases the output is equal to 1, and this particular rule is valid for even for a NAND gate having more than 2 input terminals. For example, if this particular NAND gate had 3 input terminals, so I'll draw the third terminal over here and I'll call it C. Then of course you would have introduced a third column over here, you call it C, and then of course you would have written all the permutations. There would have been 8 of them, so there are 8 rows totally, and by the end by the time you come to the last row, you would get 1 1 1. Now this is the only place where you would have got 0 as the output. All other places, all 7 other places, the output is going to be equal to 1. Of course, the symbol for y is going to be, in this case, a dot b dot c with a bar on top of it, because it's a NAND b NAND c. And with this we end our discussion of a NAND gate. The last gate that we are going to consider is a gate called the NOR gate. And the word NOR is actually a combination of the word not with OR. So not OR is NOR. And as the name suggests, the NOR gate is nothing but a standard OR gate which is followed by a NOT gate. In other words, the output of the OR gate is given as input to the NOT gate. Now the NOR gate could have 2 or more than 2 inputs, but for the sake of the example we will consider a NOR gate having only 2 inputs, like that. So this entire structure is called a NOR gate. And to draw the truth table of a NOR gate is a very simple matter, because we know what is the truth table of an OR gate. So whenever you expect a 1 over here, that is, whenever you expect the output of the OR gate to be 1, the NOT gate is simply going to convert it into a 0. And likewise, whenever the output of the OR gate is going to be 0, the NOT gate converts it into a 1. So let's try to draw the truth table of this particular NOR gate. But before that, let me draw the NOR gate in the standard way. Standard way to draw the NOR gate is to draw an OR gate like that and put a small circle over here symbolizing the NOT gate. So this would be the output, and since it's a two input terminal NOR gate which we are talking about currently, you draw 2 input terminals like that. So that's the standard symbol for a NOR gate. Now let's call these 2 inputs A and B, and the output is Y, and Y is equal to A NOR B. The symbol for A NOR B is, you first write A OR B, the symbol is of course A plus B, and you put a bar sign on top of it which stands for NOT. So A NOR B is symbolically written as A plus B with a bar sign on top of it. Now the truth table of this particular NOR gate is drawn by first of all writing the input side of the truth table, which will contain 4 rows as usual. So 0 0, 0 1, 1 0 and 1 1, and at the output we have Y. Y is of course equal to A or B with a bar. It's A NOR B, but the trick to draw the truth table is first to consider only A or B like that. So you know that for A or B, the only place where you get a 0 is when both A and B are 0. Everywhere else you get a 1. So that's A or B, but really we require the truth table of A NOR B. So it's very simple. Wherever you see a 0, you convert it to a 1, and likewise wherever you see a 1, you just convert it to 0 like that. And that's going to be the truth table of a 2 input NOR gate. So you can see that the rule for the truth table of a NOR gate is, whenever all the inputs are equal to 0, that is the only place where the output is equal to 1. Everywhere else the output is going to be equal to 0. And one must be aware that this particular rule works for a NOR gate having more than 2 terminals. For example, if I draw a 3 terminal NOR gate like that, so this is my third terminal, I'll call it C, then of course Y would be A plus B plus C with a bar on top of it. It's A nor B nor C. And in the truth table you will have a third column over here, C. So over here you write 8 rows which correspond to 8 permutations of ABC, and in the last row you have 1 1 1, in the first row you have 0 0 0. Now it is the first row which contains only zeros where you get, and in fact that is the only place where you get an output of 1, and in all other 7 rows you get outputs of zeros like that. So that's how you draw the truth table of any general NOR gate. Now these two last gates which we have just talked about, namely the NAND gate and the NOR gate, these two gates are called universal gates, and they are also called universal building blocks. And the reason is, any logical function, howsoever complicated it is, can always be constructed using only one of these two types of gates. For example, if you had only NAND gates with you, assuming that you had them in sufficient quantity, then any logical function can be realized, or one can say it can be constructed using only NAND gates. You don't require any other gate to realize a logical function whatsoever, howsoever complicated it may be. Likewise, any logical function, howsoever complicated it may be, can be realized using only NOR gates. You don't require any other gates if you have a sufficient number of NOR gates with you. Now, to make the point clear, let's consider that I have a system. I want to build a logical system in which, let us say that there are 3 inputs like that, and they are called A, B and C, and I've got some output over here which I call Y. Now it's not any ordinary output. I give it to you in the form of a truth table, and let's say 0 0 0 corresponds to Y equal to 0, and 0 0 1 corresponds to Y equal to 1, and 0 1 0 corresponds to Y equal to 0, and 0 1 1 corresponds to Y equal to 0, and 1 0 0 corresponds to Y equal to 1, and so on. So you can see that Y is not following any well-known pattern. It's not obviously going to be a single AND gate over here, or a single OR gate, or a single NAND gate for that matter, which is going to give you this type of output. It's going to be a combination of gates which you want to use inside this box, such that the output is going to be whatever desired. Of course, there are going to be totally 8 rows over here, and I've just drawn 5 of them, so you can imagine that there are 3 more. So what we are trying to say over here is, if you have only NAND gates, so you can actually realize this particular logical function. There are 3 more rows which I have not drawn. I just repeat that. You have to imagine whatever they are, it doesn't matter. If I have only NAND gates and I connect them in a certain way, maybe the output of this goes to the input of this, maybe the other input is coming from C itself, and so on. Let's not talk about the interconnections between these NAND gates. The rule is, you just put a sufficient number of NAND gates inside this box, connect them properly, and eventually you will be able to get the desired output Y. And if you don't have NAND gates, you can do the same thing with NOR gates, and that's why they are called universal building blocks or universal gates. And that's actually the reason why these two types of gates, NAND and NOR, have become very popular and are widely used in electronic digital circuits. And on this note, we complete our discussion of logic gates.